Hello and welcome to this video where we'll be covering the GCSE higher topic, proof. Now proof is considered to be a difficult topic because of the way the questions are worded. However, once you understand the fundamentals, as long as you're careful in the way that you interpret the wording, these questions actually become fairly straightforward. First, however, it's necessary to go through the type of wording that is used in the questions. Okay, so starting with the description of any integer. So all integers can be described and are described in proof as follows. Even numbers are described as 2n. This is because if you multiply any number by 2, it becomes even. Therefore 2n is proof of an even number. Or odd numbers, which of course are all the other numbers. So an even number is 2n. So if you go one beneath that, which is 2n minus 1, or above that, which is 2n plus 1, then you have yourself an odd number. So between these two categories, they describe every integer. Every integer is either even or odd. Okay, if a question asks for the sum of any two even integers, in other words, two integers that are not connected, that are not consecutive, for example, or one is a multiple of another, if there's no relationship between them, then what we can do is instead of using the unknown value n on its own, we're going to have two separate unknown values, n and m. These simply reflect two different integers. So two even integers will be described as 2n plus 2m. If the question asks for the sum of any two consecutive numbers, so the word consecutive means that one comes after the other, then there's an example shown below. This is basically of an odd integer, and then the integer that follows it exactly, which is the next one up. So the odd integer 2n minus 1 is followed by the integer 2n. Therefore, that expression 4n minus 1 represents the sum of any two consecutive numbers. If instead the question asks for the sum of any two consecutive even numbers, okay, so we start with 2n. So if our starting point is the even number 2n, the next one would be 2 above that, because that would be where the next even number would sit. Hence, that would give you, in this example, if the sum of those would be 4n plus 2. If a question asks you to prove that a number is even, what we're doing here, so what we've got here is an example of an expression, so 2n squared minus 6n plus 4. So that's just an expression that I've made up. How we can prove that that is even by factorising out the 2. You'll notice that by factorising out the 2, what we're showing is no matter what is in the brackets, that number, the overall number, would become even because you're multiplying it by 2. Okay. Similarly, if we want to prove a number that is a multiple of 3, we would factorise out the 3 for the same reason. Whatever is in those brackets, we're multiplying that by 3, so that automatically is in the 3 times table. It is a multiple of 3. Finally, and this is the one that's one to keep an eye out for, if you haven't seen this sort of question before, prove a number is a square number, you might think, how on earth can we do that? Well, the way to do that is simply to get your expression, whatever your expression you're left with, to factorise that expression. And when you do so, you should note that there's only one factor. So here, the factor is n plus 4. And if you factorise it out, that becomes, so n plus 4 in brackets, followed by n plus 4 in brackets, simplifies to n plus 4 in brackets squared. So let's see if we can apply some of these principles to questions. The first one we've got here, it says prove algebraically that the sum, okay, so the sum of any two consecutive numbers, any two consecutive numbers, or integers I should say, is always odd. Okay, so we'll come to that proof at the end. So the first thing we're going to do is formulate this expression in each of these questions. Okay, we've got the sum, so sum means adding up, and we've got two consecutive integers. So again, if we use the example of 2n minus 1 as being the first integer, the number that comes after that, as described in the previous slide, is 2n. So when we add these two up, the sum of those, we need to prove that it's an odd number. So if we add those up, what we get is 4n minus 1. And we can prove that that's an odd number. And the way that we do that is we factorise this 4n by taking the 2 out of it. Okay, we're saying that 2 can be factorised out of the 2n. That expression there itself shows, the one that I've written so far proves that this is even. And you might say, well, I can see that it's even because I know that 4n is a multiple of 2. You need to show that. So the way we show that is by taking the 2 out of the brackets like so. So that is an even number, and any even number plus or minus 1 is an odd number. So therefore we proved that this the result here will always be odd. The next question, it says, again, prove the sum. And this time it says any 3 consecutive even numbers or even integers is always a multiple of 6. So we've got 3 integers this time. They're even integers, so we'll start with 2n. So that's the first one. I'm putting these in brackets. This becomes important in particular when we're talking about the difference between 2 integers, because obviously if you're adding or subtracting, so if you're subtracting, that does impact everything that is inside a bracket, but we'll come to that later on. So the sum of any 3 consecutive even integers. So the first one will be 2n. The second one, again, as described before, that's going to be 2n plus 2. That's 2 values after the initial integer there that we've got. The next one, excuse me, the next one is going to be 2n plus 4. We're simply going up by 2 each time. And all we do once we've got this is we simplify this expression to prove that it's a multiple of 6. You can see that there's 2 for 6 n's. So we've got 6n there. And then we've got plus 2 plus 4. So that's going to get us to 6n plus 6. To prove that it's a multiple of 6, what we're going to need to do in this situation is factorise out the 6. And you can see that in this expression, that there's 6 is a multiple of both of those terms. So we're going to factorise out the 6. So 6n plus 1 in brackets. That is sufficient to prove that algebraically, that this final expression is a multiple of 6, because whatever's in the brackets, we're multiplying by 6. So it will be in the 6 times table. Next question, it says prove algebraically that the sum of the squares of any 2 even positive integers, so any 2 even positive integers is always a multiple of 4. So again, we've got the sum, so that's going to be adding any 2 even positive integers. So the first even positive integer we're going to have is 2n. Okay, and the second one will be 2m. But as it says, the squares, so the squares of any 2 even positive integers, so these numbers will be squared. So that one will be squared, and this one will be squared. Okay, remember that 2n in brackets squared, that is the same as 2 squared n squared. Okay, we're literally squaring each of those terms inside the brackets. So we've got 2n squared, that gets to 4n squared plus 4m squared. Okay, and we need to prove that it's always a multiple of 4. So all we're going to do here is we're going to factorise out the 4 for this one. And we get 4 bracket n squared plus m squared. No matter what those numbers are, inside the brackets, we multiply it by 4 to make it a multiple of 4. Prove that the sum of the squares of 2 consecutive odd numbers. So again, we've got the sum of the squares of 2 consecutive odd numbers. 2 consecutive odd numbers. Okay, so it's a sum again. So we're going to add. We've got 2 consecutive odd numbers. So let's take the first odd number, 2n minus 1. Put that in brackets. And the one that's consecutive to that, the one that comes after 2n minus 1, that's an odd number, will be 2n plus 1, because we're going up by 2 from our initial number. And they're the squares again. So again, we've got to do this one. So a little bit more work in this one, but as long as we remember some principles, we're fine. So 2n minus 1 in brackets squared, remember that that is the same as 2n minus 1 in brackets repeated. So there are two two brackets of 2n minus 1. Okay, and if we expand those brackets, what we get is 4n squared minus 2n minus 2n, and just be careful with the negative number. Minus 1 times minus 1 is plus 1, so be careful with that one. So we end up with 4n squared minus 4n plus 1. If we do another question here, sorry, the other expression over here, so 2n plus 1 in brackets squared, that's going to be 2n plus 1 in brackets, followed by the same thing. Okay, and if we expand this one, I'll just jump to the final bit for this one. So 4n squared plus 4n plus 1. So the first expression that we've got, and we'll put these in brackets, 4n squared minus 4n plus 1 plus 4n squared plus 4n plus 1. Okay, 4n squared plus 4n squared gets to 8n squared. Minus 4n plus 4n, that means we can cancel off these ones. Okay, we're going to cancel these ones out. So those no longer are in our expression. And then we've got plus 1 plus plus 1, which gives us plus 2. So we've got 8n squared plus 2. The question asks for, we need to prove that it's 2 more than a multiple of 8. So the final stage of this is to prove that the first part of the term is a multiple of 8. So we're going to put that in brackets outside the n squared. That proves that no matter what our value of n is, we're timesing it by 8 to make it a multiple of 8. And then we're going to add 2. So 2 more than a multiple of 8, which gives us this answer. The next one says prove that the difference between the squares of any two consecutive integers is equal to the sum of these integers. So this time we've got a difference. Okay, we've got the difference. So we're going to try and put the larger number first and then the smaller number second. Okay, so slightly more to think about. Between the squares of any two consecutive integers is equal to the sum of these integers. It actually doesn't matter which way you put the terms around though. But what is important is you apply the subtract element of it correctly. So we've got the squares of any two consecutive integers. So as long as they're consecutive, so they are linked to one another because one is above the other. So again, what we'll do is we'll start with 2n. So we'll do 2n squared. That's our even integer. And we're going to take away the one before it. Okay. So 2n minus 1 in brackets squared. And eventually we're going to prove that this is equal to the sum of those integers. Okay. So this is the first stage of the workings. Later on, we'll also have to prove that it is the same as the sum of those integers. Okay, so the sum of those integers will be 2n plus 2n minus 1. Okay, so that's going to be the stage 2. We're going to prove that the answers for each of these calculations are the same. So the squares of any two consecutive integers. So again, all we're going to do now is we're going to do the algebra that we need to do. So 2n squared gets us to 4n squared. Let's do 2n minus 1 over here. So that is the same as this one. So 2n, this is 2n minus 1 in brackets squared. Okay, and if we multiply these out, we did this on the previous slide. So that gets us to 4n squared minus 4n plus 1. So what we're going to do, so make sure you put this one in brackets. I didn't put this one in brackets. Okay, so that was our first term. This term over here becomes 4n squared minus 4n plus 1. So we've got to be careful here because we're subtracting. So 4n squared subtract 4n squared means we can cancel these ones off. Okay, we're subtracting minus 4n. Okay, two negatives become a positive, so that becomes 4n. and we're subtracting positive 1. Okay, we're subtracting positive 1, so that becomes 4n minus 1. So that's our answer to the first part of this question. And the second part is we're going to add these two expressions together. So these were our two integers that are consecutive. Okay, and if we add those together, then we also end up with 4n minus 1. So we proved that we proved the statement that has been requested of us. The next bit, it says n is an integer. Prove algebraically that the sum of those two expressions that are listed, that's shown, is always a square number. So what we're going to do is we are going to simply add these two. So we've got this one to begin with, and then we're going to add on the second one. So those two in brackets. And so that basically, if we multiply these out and add them together, we're going to have n squared plus n plus 1. So we end up with n squared plus 2n plus 1. And this is where it's worth remembering what proving a square number looks like. And as previously stated, to prove this is a square number, all we do is we factorize out this expression here. So that is the same as n plus 1, n plus 1. And that can be simplified to n plus 1 in brackets squared. Thank you for watching. If you found this video useful, please like and subscribe for more. Or if you're interested in one-to-one tuition specialising in foundation or higher GCSE exam preparation or functional skills, please click on the link in the description and submit an inquiry at apexmaths.net.